Welcome back friends for another lecture on quantum field theory and quantum entanglement. So we were looking at the interaction picture and we were looking at self interactions of the scalar field. So along the way we encountered several things like essentially the propagator and the interaction picture. We derived the entire S matrix and so on. So now so there is this thing called, after deriving the S matrix, we have written everything in terms, we also encountered normal ordering and everything. So we were looking at the properties of the propagator which I am assuming that you already know it in your relativistic quantum mechanics course, but anyway we will cover it again. Essentially it is a time order product essentially given in terms of this. So this the propagator here is given time order product of phi x phi y essentially of the scalar field, as you can see on the screen, is equivalent to the normal order product of phi x phi y plus the propagator. That is the propagator. The propagator here I am denoting it as delta f x minus y. In a more general fashion essentially you can write this is the so this in a more general fashion, this is what the result is essentially. So today what we will look at is I will slightly go back a little bit in a free field theory essentially. This is all free field theory again, while we are still doing interaction picture. Because of the S matrix we always, as you know, only at the interaction point we use the interaction picture and rest of the places we only use free fields, as we have seen essentially. Because if you remember in your previous lectures that we are always dealing with free wave functions essentially and free field solutions, whereas the interaction point we are so it's the interaction picture is a mixture of both Heisenberg and the Schrodinger picture. And okay, this is so if you remember correctly that interaction picture is a mixture of Heisenberg and the Schrodinger picture. We typically use the Schrodinger picture for the fields, and for the interaction points we use essentially the Heisenberg picture essentially. So at that point only at the interaction point we use the Heisenberg picture, and so here essentially we looked at the scalar field operators essentially. So phi star square essentially, which is phi 4 theory. So we looked at how does it work, and then along the way we hit upon the propagator, and this propagator is a free propagator. Okay, this propagator. Okay, so today we will continue our work on I will continue our discussion on the propagators a little bit more. Okay, and along the way we will see some properties of these propagators essentially. So we will continue with our understanding of the propagators. And okay, so how do you write okay, just to revise, I think most of you know what a propagator is, as the propagator is is typically you start with the question, what happens if you have a particle at some space time point phi of x. So and the question is what is its amplitude at a point say phi of y, say phi. So okay, so the basic idea okay, the basic okay, this is completely connected with the causal structure of the theory essentially. If you remember we are in a relativistic theory, as you will know, as you know very well that we are in a relativistic theory, that we want all the amplitudes to dominantly lie within the light cone, okay, to lie in the light cone essentially. So this is the light cone, so this is essentially x is equal to t, this is the light cone, this is the forward light cone, this is the backward space essentially. So we want all the amplitudes to lie within the light cone and to die off systematically outside the light cone. We do not want a causal amplitudes, in the sense that we do not want acausal transmissions, meaning which are transmissions which are unphysical. Okay. So, we can calculate this amplitude. So, we can so this is closely related to the causal structure of the theory. That means what? That means a causal structure, it means that we want everything to lie within the light cone, meaning okay. The causality violations means you have some transmissions which are happening beyond the speed of light, essentially transluminal propagations. Such propagations should die off naturally. We do not want, they have to be completely suppressed, they have to be 0. So, what we now, how will you calculate this quantity, which is this quantity, which is the amplitude of a point of a particle at x, given a amplitude at a particle at x, what is its amplitude at a particle at when it is at y. So, we will just define if an at a vacuum expectation of phi x phi y essentially, and then this you can compute it, because now you have written it in terms of A dagger products, which we have known, which we have in the modes essentially, and let us write it in terms of this mode, and this gives me this now this you can do. Now this is looks very similar, this is the exactly the same function which we wrote on in the previous class essentially in lecture number 12. So, this is given by dqp 2 pi cube 1 by 2 e power minus pi x minus y, and this is nothing but your propagator. This is nothing but your propagator. So, this function is called the propagator. Okay. This function is called the propagator. Of course, there is some repetition, but it is fine, I think we should find. Now, does it have the properties? What we wanted is that what is the causal structure? Essentially, does it have the required properties what we want essentially? So, for space-like separations, meaning for time-like it should be proper, meaning this amplitude should be good. For space-like separations, so for space-like separations, okay. So, this you can check that d of x y is non-zero, but it falls off like e power minus m mod x minus y. Okay. So, it just really falls off very rapidly, it is exponentially suppressed essentially. Okay. So, maybe this bar should be, this should look like a minus sign. Okay. So, for space-like separations, it's still non-zero. It's non-zero. This is important to note essentially. It's non-zero, but it's highly suppressed with the distance x minus y essentially. So, it decays exponentially outside the light cone, but it's still non-zero. Okay. Maybe I'll write it down here. Okay. decays exponentially outside the light cone, but it is non-zero. Now, if you actually, now you will say, oh, if you are worried about but the point is that it's you are worried about, oh, it's still there, what about its contribution? Say for example, the contribution coming from the space-like separations to in a process. Now, we will soon move to calculating process like what we have seen in S matrix, right. In an S matrix, what we saw that the propagator will play a role because it contributes also. Now, what about contributions coming from space-like separations in the S matrix essentially? It turns out they cancel out essentially, they cancel out for a real scalar field essentially. We will see an example, say for example, real scalar field propagator, say for example, if you have Yukawa force or something, something like that, or any scalar propagator, it turns out that the space-like separations will just cancel out essentially. They just their contributions goes to 0, they do not contribute, and for this it becomes more interesting for a charged scalar field. Okay, and now the key point to remember is that if you have a space-like propagation from x to y, you can also have a propagation from y to x. It is sort of symmetric between x and y essentially. So, you have an x to y propagation and y to x propagation. So, the x to y propagation and the y to x propagation cancels out essentially. The x to y propagation and the y to x propagations, space-like propagations will cancel out outside the light cone essentially, okay, outside the light cone. Now, for a real scalar field, it is just the particle and antiparticle are the same. For a charged scalar field, the antiparticle is the backward propagation of a particle, as we have seen essentially under the Feynman-Stackelberg interpretation. The antiparticle is the backward propagation, meaning t goes to minus t essentially, the backward propagation of the particle. So, the space-like contributions of the particle and the antiparticle cancel each other. For a charged scalar field, the space-like contributions will just cancel each other essentially. So, in particular, now this df is called the propagator in general, but we also know the prescription which we use actually in the calculation is called the Feynman propagator. So, what is the Feynman propagator? The Feynman propagator, this plays a very important role in interacting field theories, takes care of these issues for say for a x0 greater than y0 and for y0 greater than x0 essentially. It just takes care of essentially, it introduces the time ordering for the propagator essentially, it introduces the time ordering in the propagator. So, the Feynman propagator has the following properties. Okay, it is defined as follows. So, the Feynman propagator del f x minus y is equal to again time ordered product of phi x phi y of 0. So, the main difference say okay. So, between this what we have seen and this is a time ordering. Okay, this is the main difference between the Feynman propagator and the ordinary propagator. Now this is defined as follows. For x0 greater than y0, x0 is a time component. Okay, if the time component of x0 is greater than y0, this is the Feynman propagator, which is defined in this particular fashion. This is defined as y minus x for y0 greater than x0. So it is giving you a direction. Okay, it is giving you a direction in the D, essentially in this function. Essentially, it's giving you a direction in time in this function, essentially. So when you are computing this function, it is telling you which part of the function, which kind of function which you had picked up, depending upon whether you had to pick up x goes to y or y goes to x, depending upon what is the time between these two, essentially. So what does time ordering do? Time ordering tells you that if something is occurring at a later time, if y0 is greater than x0, so it should always be placed on the right. Just like normal ordering, where all the annihilation operators are always on the right, essentially. So similarly, the time ordering tells you that time ordering, we have seen already this thing, places all the operators, all the space time points at later times towards the right. So on the right, okay, not even on the right. Okay. So for example, this I am repeating this definition which we have seen already. So time of phi x phi y is equal to phi x phi y for x. I am going slightly faster because we have covered this thing. Okay. Now there is a for this Feynman propagator, essentially there is a momentum representation. Okay, momentum representation which is highly useful. Okay. Because we do most of the calculation in momentum space, essentially in the computation, okay, which is highly useful, is this, that d of f delta f x minus y is equal to d power 4 p 2 pi power 4 I p square minus m square e power minus I p x minus y. This is just the momentum space representation of the propagator. Now you see that we have p square minus m square. It's like, if you look at this, this is nothing but the inverse of the equation of motion. Okay, it's nothing but the inverse of the equation of motion. So what we have done is we integrated over the 4 momentum. Essentially what we have done is we have integrated over the 4 momentum of this function, essentially of this function. So we have been doing only integration over 3 momentum so far, but here you put in an integration over d power 4 here, essentially. Okay. Now this gives us a choice, essentially. So this gives us a choice in say in p0. Okay, let me put it p. We had to make a, let's make it when we do this integration, we will make a choice in p0 about the pole in p0. So now if you see this, p square minus m square has poles at p square is equal to m square, right? Essentially you have poles at p square is equal to m square. Now in the p0 and the complex p0 plane, essentially you have pole at plus Cp and at minus Cp. It's equidistant or may not be. okay, let me make it equidistant. So, okay, roughly minus CP. Okay. So, when you close the contour, you have to pick up one of the poles. Essentially, you have to pick up one of the poles. The point is that you want to pick up a pole when you are going in the so you want to pick up a pole either at this pole or that pole. So, when you are closing clockwise, you will take one of the poles. When you are closing anti-clockwise the contour, you take the other pole. That is the basic idea essentially. When you are closing on the clockwise, you take one pole. So, you can take along the real axis. Let me use some other color. So, when you are okay, going the other side, you close the contour with the other pole essentially. Okay, so okay, let me explain you this a little bit more. So, what we have, there is a pole in p square plus m square. So, what you want to do is 1 by p square minus m square is equal to 1 by p0 square minus EP bar square, okay, that is equal to 1 by P0 minus EP bar minus 1 by P0 plus EP bar. So, the residue at the pole at P0 is equal to plus minus EP bar is plus minus 1 by 2 EP. Now, this depends whether we want to pick up the plus half or the if you are picking up plus EP bar, the residue is plus EP. If you are picking up minus EP pole, it becomes minus EP essentially. So, when we close the contour, x0 is, did we write x0 as x0 x0 greater than y0, we close the lower half plane where P0 goes to infinity and this will pick up P0 is equal to plus EP pole essentially. So, again looking at the structure essentially, so you see that when you close the contour at the lower half plane, say for example in the red line, and then take this all the way to imaginary infinity, P0 imaginary P0 is goes to all the way to minus I infinity. Okay. What will happen is that the integrand vanishes, the integrand vanishes e power minus I P0 x0 minus y0 goes to 0, okay, because P0 goes to minus I infinity, it just goes to 0. Then this picks up the pole P0 is equal to plus EP, okay, and in that case you have the propagator delta f x minus y is equal to integral d cube p 2 pi power 4, if you do the P0 integral, minus 2 pi I by 2 EP bar I e power minus I e p x0 minus y0 plus I p bar x minus y. Okay, maybe let me just re-express it. Essentially d cube of p 2 pi power 4 2 pi minus 2 pi, which is the residue theorem, bar I e power I e p x0 minus y0 plus I p bar x minus y bar. Okay. So, in this case, when x0 is greater than y0, you pick up the EP, you close the lower half plane, picking up this, and this gives me d cube p. So, you can do curve by cube 1 by 2 EP I minus 1 plus 2 pi cancels. So, this gives me e power I p dot x minus y this is nothing but d of x minus y. Okay. So, but this is time ordered, which is the final in contrast. Okay, this is in the time ordered essentially. So, this is the okay. So, what we did was that the integrand goes. So, the important point is that when the integrand goes to when you close this pole essentially, when you close this pole, when you choose the contour and we will choose one of the poles essentially in the x greater than x0 greater than y0. In the y0 greater than x0 case, what we will do? We do the reverse. Essentially, we have delta f x minus y is equal to, so we choose the upper half plane and redo the exercise, and that gives you a minus sign here. Okay. So, P0 is equal to minus EP bar, and that gives you a half EP as the residue. Okay. It gives you the residue, and so delta f would be, in this case you can work it out essentially. So, again it will give the same thing, you have the same form. Finally, okay. So, once again we reproduce the Feynman propagator. So, whether x0 is less than y0 or y0 is less than x0, we will end up reproducing the Feynman propagator, which because we choose the contours in such a way for the two residues that you only pick up one of the poles, and so so that way you reproduce the same propagator for both x greater than y0 and y greater than x0 essentially. So, instead of specifying, so this specification is of the contour is called Feynman prescription, and that is the reason why this propagator is called the Feynman propagator. So, in principle, without actually telling what is the contour, so all this, the choice of the contour is understood, and this entire exercise that meaning now when you are doing calculations, it becomes difficult to say that okay, what I mean is that you are choosing this particular contour for each of these cases essentially when x0 is equal to greater than I0. you choose the lower contour for y0 greater than x0, you choose the upper contour and then close the contour in such a way so that the integrand vanishes and you take the residue. Instead of saying all that stuff, so you just say something simpler, you denote it by so this I epsilon tells you this is epsilon is this small distance, essentially this is a small distance, this is the small distance, this is epsilon, okay, this is epsilon essentially. So we are taking this small epsilon here essentially. So this epsilon tells you that you make the correct choice of the contour depending upon x0 is greater than y0 or y0 is greater than x0. So this forms the so called the Feynman propagator essentially. This is the Feynman propagator, and this is how we typically denote the Feynman propagator in all the interaction theories essentially. And when you are calculating process and decays or cross sections and everything. So we assume just by putting this I epsilon in the notation, we assume that we choose the correct contour, and that will settle all the integrities which we had discussed over all this lecture essentially. So the choice of the contour, the time ordering of the product, the problems with the space-like separation, and so on, so essentially. Okay, I hope this is clear. Now there is one more thing I want to mention. Okay, so this is something. There is another way of understanding propagators. In fact, this is the method which we did in relativistic quantum mechanics when we are doing relativistic quantum mechanics and everything. So one way is actually what we have done in this lecture series so far, expand the wave functions in terms of modes essentially, momentum modes, and each momentum mode is replicated with a harmonic oscillator, and then you when you do this mode expansion into AA dagger harmonic oscillator operators, and then put it back, take the time order product between the amplitudes, and then you have the derivation of the propagator, as which we have done. In the relativistic quantum mechanics course or any other earlier way, what we did, we derived the propagator as a Green's function. Okay, the propagator is as a Green's function. So the point is that we derived the propagator as a Green's function of the Klein-Gordon field equation, sorry, not the field equation, in relativistic quantum mechanics course, okay, quantum mechanics. So they are equivalent essentially. The basic idea, what I want to tell you, there we didn't care, we didn't talk about time ordering and everything, but we did that, but we didn't do it in terms of mode expansion and everything. But there what we did was del square T minus del square. So we wrote down the Klein-Gordon equation, m square delta f x minus y is equal to minus I del power 4 x minus y. So what we said was the propagator is a solution of the Klein-Gordon equation with a delta function source. Okay. The propagator, okay, this is something which you may have known in your relativistic quantum mechanics course, but this is just a repetition. The propagator is the solution of the Klein-Gordon equation with a delta function source. Now, how do we check it? Now, you know the equation for the delta function, you can put it back into this, and you know how to write the propagator. Of course, you can easily check it, delta square minus square plus m square. Now that we have derived the propagator, delta f x minus y, so this is equivalent to integral d power 4 p to pi power 4 minus I p square minus m square. Now, in the momentum space delta t square, this entire thing just becomes p square plus m square. So, e power minus I p x minus y. So, you see that the propagator is nothing but the inverse of the equation of motion. Okay. So, this is very clear that this is nothing but d power 4 2 pi power 4 e power I p x minus y. So, that is nothing but I delta power 4 x minus y. So, we are closing the thing essentially that we are closing the thing that the propagator, what we have studied in the relativistic quantum mechanics course and everything, and this propagator which we have derived using the field theory mode expansion essentially. In this case, we have not done anything essentially. This is almost like classical field theory, that you just put in a delta function source and derived the propagator's solution essentially when we did this. Okay. The derivation in the relativistic quantum mechanics course, but we get the same equation of for the propagator, but now with a quantum field theory interpretation, in the sense that you can expand it in terms of the modes, essentially the fields in terms of the modes. We are dealing with the scalar fields so far with the real scalar fields and complex scalar fields. We did it with the modes, and if you have complex scalar fields, you have two different operators A and B, ladder operators essentially. So, creation and annihilation operators, put it back and then take the time order derivation, time order product of phi x phi y, and that gives you the propagator equation essentially. So, and then we will also looked at the Feynman prescription. So far we have now sort of collected almost all the ingredients required for calculating a simple process in relativistic field theories essentially. We have derived the propagator solutions, we have now the interaction picture. So, we will try to do one or two examples in the next class before going to fermionic fields. Okay. So, let me stop here and I will meet you soon in the next class essentially. Okay. Thank you very much.